Well, hello to who's ever listening. We're going to talk today about statistics and probability, and in particular, I want to look at calculations for variance when we are studying measures of spread or central tendency in statistics, and then we're going to try to connect that to discrete random variables where we're talking about probability distribution functions. So what I'd like to point out today is that what you learned in statistics with variance is going to apply directly to what we're doing now when we talk about the mean and the variance of a probability distribution function. So to put all those pieces together, I'm going to start with a random make-believe game. We have right here a spinner, and there's different outcomes. It looks like the one seems to have disappeared. Oh, there it is. We have the spinner, and there's a variety of outcomes, 0 through 4, but each of the regions is a different size. So, for example, there's a 43.8% chance of the arrow landing in the 2, for example. So we spin and spin and spin and spin, and let's say we did this 16 times, and this is, of course, a perfect world. We ended up with this specific distribution. That is to say, when I spun 16 times, one of the times I landed on the 0, which makes sense. It didn't happen very often. Twice I landed on a 4, which happened, twice as frequently. It looks like 4 has twice as much space or more. So basically, these are the theoretical outcomes if we were to spin this 16 times. That's what should happen. Now, what we learned in standard deviation was a sort of a theoretical concept, and then it became shortcutted. And so I want to show you the original theoretical concept. What we're trying to do in looking at standard deviation is we're looking at a spread of data. So here you can see the distribution table written as a bar graph. And we can see each of the distributions laid out here. For example, there's 7, which is halfway between 8 and 6. So if we were looking at the mean should be somewhere around 2, because that's generally the center of this distribution from 0 through 4. And if I was to look at the standard deviation, I would expect that to be somewhere around 1 above or below. That is to say, the majority of the data fall between 1 above or below the mean. So, as for the calculations, what we're trying to do, if you recall, when we're finding a standard deviation, is we are trying to find the average distance away from the mean of the data. In other words, we're trying to figure out how spread out the data are. Normally, we would actually look at the deviations from the mean, but sometimes we have stuff that's below the mean, and sometimes we have stuff that's above the mean. And if we were just to add up the deviations from the mean, we would always end up with 0, because the mean is the middle, and the deviations from the mean average out literally to 0. So what mathematicians decided to do was to first calculate the deviations from the mean, and then square those deviations so that they're always going to be positive. And then we divide by the number of trials. In this case, there were 16 trials, and that will give us the average squared deviation from the mean. If we take the square root of that whole sum, we're going to get the standard deviation, which is the unsquared, or the square root of all those squared deviations. It's kind of a fuzzy little logic, but it's the way I always remember it, is we first have to figure out the sum of the squared deviations. So we have all the deviations from the mean. We square all those deviations from the mean to make them all positive. We divide by the number of trials, and then when we're done, we can take the square root of the whole thing, and that's going to give us our standard D. So, computationally, this can become a little bit of a hassle. First thing we have to do is recognize that in a frequency distribution table, the outcome of 0 happened once, which means there's a total of 0 added to our outcomes. The outcome of 1 happened 3 times. The outcome of 2 happened 7 times, so there's 14 added to our outcomes. The outcome of 3 happened 3 times for 9, and 4 happened twice for 8. So 34 is the sum total of all the numbers that were added up after we spun the wheel 16 times, which means the average number when I spin the wheel is going to be 2 1/8, or 2.125. Which makes sense when you look at the graph. Most of our data fall at 2. It makes sense when you look at the spinner. It makes sense that mostly we're going to land around 2. And then we also notice there's a little bit of a left skew here because there's a little bit more happening to the right of the mean than there is to the left, which is why the mean is slightly larger than 2. Anyway, now in order to use this formula, which is again the one that I can always remember this formula because it makes sense to me, but it's a little bit of busy work, because the first thing I have to do is I have to figure out the deviation from the mean, and in this case 0 is 2 1/8 below the mean of 2 1/8, and that happened once. There's our frequency. Then we have the number 1 is 1 1/8 below the mean, and that happened 3 times. 2 is 1/8 below the mean, and that happened 7 times. And 3 is 7/8 above the mean, that happened 3 times. And 4 is 1 7/8 above the mean, and that happened twice. So if I add up all of these numbers, that is going to be the sum of the squared deviations. So, or no, I'm sorry, these are the deviations. Then I'm going to have to square those deviations. Sorry, that's where these numbers come from. And again, the squared deviation happened once, the squared deviation happened 3 times, this squared deviation happened 7 times, and this squared deviation happened 3 times, and so on. So already, hopefully you can see how this is becoming a little bit like tedium, a little bit like busy work. I have to add up the squared deviations from the mean. So all of these numbers I have to add up, and it creates this long chain of fraction-y fraction math. When I add them all together, I get 17 3/4. Sparing you all the pain and heartache of having to do all that data crunching. It's not a big deal. So I have enough information now to utilize this formula, which says we're going to take the sum of the squared deviations and then divide by the total number of outcomes, and that's going to give us my variance. That turns out to be about exactly 1.109375. If I take the square root of that value, that gives me my standard deviation of about 1.05. Once again, it says most of our outcomes are going to be around 2, and the majority of the data are going to be above or below 2 by 1. So to say most of the data are 1, 2, or 3. Again, look at the graph, that's obvious. That's not why we're here today, though. I want to connect this to probability, but before I do, I want to remind you of a computational formula. This is a shortcut, and it's provable. If you were to take this formula and rearrange it in a bunch of different ways, you can end up with this shorthand formula. It's a little bit of a high-level statistics for you. But this is a computational formula. It doesn't make logical sense like the average sum of the squared deviations, or the average squared deviation makes sense to me, but this, I don't quite get what it says. Now, the way that we would read this if we were trying to translate it is we're going to take the average of the squared outcomes, and then we're going to subtract the square of the average. So the average of the squares minus the square of the average. It's a mouthful. But it's really easy to use, because what you do is you get your frequency distribution table, you square your outcomes, and then you multiply your squared outcomes times your frequency, and then we divide by 16, and that will be the squared, or the average squares of x. Just to point that out again, see 1 squared is 1, that happened 3 times. 2 squared is 4, that happened 7 times. 3 squared is 9, that happened 3 times. 4 squared is 16, that happened twice. So the reason why we have to multiply by the frequency is because the outcome 4 happened twice, the outcome 2 happened 7 times. If we didn't multiply by the frequency, then we would be assuming each of these outcomes happened only once. Anyway, we find all of the squares of x and add them up, and then when we divide them by 16, we now have the mean, or the average, of the squares of x, 5.62. Recall that the average itself was 2.125, and this formula says then we're going to take this number, 5.65, and we're going to subtract 2.125 squared, and in so doing, we get the exact same results that we got in the previous exercise. So to show you, before what I had to do was I had to multiply the deviations from the mean. I had to square the deviations from the mean, multiply them by the frequency, add up all the total, divide by the number of trials, and that gave me my variance. Now all I have to do is take all my x's, square them, count up all the total number of squares, and divide by 16. That's the first part. The second part is we take our mean, square it, and subtract, and we get the exact same outcome. So I hope you can recognize all of this work was required to find the variance compared to all of this work. It's far less time consuming, far less tedious. Now, what does this have to do with probability? I'm going to change the experiment here and say that this is not me spinning the wheel 16 times. Rather, I'm going to spin the wheel infinity times, and then we're going to study the probabilities of each of the outcomes. So this is the theoretical probability of all the outcomes, and that is to say 1/16 of a chance of getting on the 0. I have a 7/16 of a chance, so just under a half, a 50% chance of landing on the 2. Makes sense. The yellow here is less than half the circle, only slightly, so we should have less than half a chance to land there. What you'll notice, though, is this is my frequency from the previous divided by 16, and this is my frequency divided by 16, and my frequency divided by 16. So basically, if I take all of my outcomes from the previous frequency distribution table and divide by the number of trials, it becomes a probability instead of a frequency. So these all used to be 8, 6, 4 on my scale here. If I divide all those by 16, now each of these bars represents the probability of the 2 or the 1 or whatever. So in the textbook, it says that you can calculate the variance of a discrete probability distribution function, which is what this is, by doing e of x squared minus e of x squared. That looks familiar. That looks like the sum of the squared deviations minus the square of the average. That's exactly what it is. It's the same formula. It just looks a lot, more mathy. But just to show you how simple this is, and by the way, I could, if I wanted to, grind this out using the OG definition of variance. I could use this formula to calculate the variance, but what the authors are trying to say is nobody does that. So instead, what I'm going to do is I'm going to take my probability distribution table, and I am going to multiply x times the probability of its outcome, put that in a column, and then I'm going to take x squared and multiply it by the outcomes, by the probability of those outcomes. So when I add up all of these numbers here, that is literally my e of x. And what you'll notice is, previously, I had to add up all the numbers, they added up to 34, and then I divided by 16 and got 2.125. Now over here, I add up all the probabilities, and it's automatically my mean, because you can see I divided by 16 ahead of time instead of dividing by 16 at the end. So going from a frequency distribution to a probability distribution is simply a matter of dividing by your number of trials ahead of time instead of afterwards. So finding the average is so much easier because, I don't know what happened here. There, I need the red arrow. What happened here is so much easier because I already have the divided by 16 part, so all I have to do is multiply these together, add this column, boom, I got e of x. X times the probability of x all added together. So that's an easy calculation. Furthermore, I just have to take the x outcome and square it, the probability, the outcome squared times the probability. So we're going to take 1 squared times 3/16 is 3/16, 2 squared times 7/16 is 28/16, 3 squared times 3/16 is 27, and 4 squared times 2/16 is 32/16. Now I'm going to add all these together, and that is literally the sum of the squares. And so that's the e of x squared, which is what this says. This is the sum of the squared x values times the probability of that outcome. That's here. I can find my variance as e of x squared minus e of x squared, which is 45/8 minus 17/8 squared. You're not going to believe the number that comes up here. Bam, 1.09375. And then I take the square root and I get 1.05327. So, very brief summary here if I can. What happened here is I was calculating the standard deviation, or the variance in the standard D, using the long form formula, and it turned out to be tedious. Then I discovered in frequency distribution there's a shortcut formula which makes it much, much easier to compute. Now we're studying probability distribution functions. The only difference is we divide by n ahead of time, but the calculations themselves are even simpler because of dividing by n ahead of time. All I have to do is add up this column, square it, add up this column, and then I subtract the two, and I get my variance. So I hope you find that helpful. Sorry if it went a little long. Thanks for watching. Have a great day.